Okay, good morning everybody. So, if you don't know, you have an exam 2 days from now on Wednesday. So let me talk quickly about that. Same format as before. Take home. 9 a.m. to 9 p.m. Submit your solutions to the exam problems as a single PDF file. The software in Blackboard is really painful for me to use, especially if you guys submit like 6 different PDFs. I have to like go in and like pre-render each page, and it takes like 3 times as long to do those exams. So please submit it as a single PDF. If you don't know how to get it all into a single PDF, just email me and I'll give you some directions. There is a practice exam posted on the Blackboard. I recommend that you do it. There's a solution guide to the practice exam on the YouTube channel. The YouTube channel also has a video listing all of the things that you should know from 2.3 to now. Okay, so the exam will cover everything that we've done since the last exam up until and including today's lecture. Any questions about the exam at all? It's basically going to be the same deal as last time. Yeah?
I'm holding a review session tomorrow to 5:50, so it's an hour and 50 minutes. So we'll be through Blackboard and have a link up there.
Excellent. So there's an extra review session. It's going to be a little bit longer tomorrow. That's with Aaron. I also have office hours today from 12 to 1. Okay. Well, we got to go back to 4.3 because I didn't quite finish this problem and I wanted to do it because I think it's instructive. So our goal is to take this function e of t, which describes the energy expenditure of some bird which is spent foraging, and we're supposed to find the foraging time that minimizes energy expenditure. Okay? So, the quantity which we want to minimize is the quantity e of t. Okay? The quantity e of t. And we're supposed to find all of the critical points of E on the interval from 1 to 24. So how should I look for critical points?
You're going to find the derivative of the equation and set it to 0?
Yes, very good. We're going to take the derivative of this equation and we're going to set it equal to 0. So first of all, let's take the derivative. What are we going to get? We'll get e prime of t is going to be equal to 0.25 plus 2 times 1.7 times t to the negative third power. Did I lose anybody there? I expressed 1.7 over t squared as 1.7 times t to the negative second power. You know what? I missed a negative sign here. This should be a minus now. Okay, and then the power became 1 less. So that's 0.25 minus 3.4 over t cubed. And we want to know when is that equal to 0? Okay, so we're just going to solve it algebraically. We'll move the 0.25 over. We'll wind up with 0.25 t cubed equals 3.4. Divide by 0.25, that's the same as multiplying by 4. Glad I brought my calculator today. 3.4 times 4, 13.6. So that's telling us that t is going to be the cube root of that. Just 2.386967 dot dot dot. Okay. Are there going to be any other critical points for this function? Let me ask you this. Is e of t a polynomial? A couple people shaking their head no. Can anybody tell me why it's not a polynomial? Yes?
Because t has a negative power.
Very good. The second term here, the power on t is not a non-negative integer. It's a negative integer. So this is not a polynomial. Okay, so what is the point of this not being a polynomial? Is that going to create any trouble for us? Yasmin?
Things that do not exist are also critical points. We need to find if there's any that don't exist on this function.
Yeah, very good. So what Yasmin just pointed out is, since this is not a polynomial, we have to be a little bit careful and consider the places where our derivative might not exist. Now we computed the derivative. We got 0.25 minus 3.4 over t cubed. Are there any values of t for which this function doesn't exist or is undefined? Alice?
Would be 0.
Yeah, t equals 0 is a problem. I can't do 3.4 divided by 0 cubed. Okay? So, the derivative does not exist at t equals to 0. However, we're asked to find the global minimum and maximum of this function on the interval 1, 24. We need to find all of the critical points in this interval. Since 0 is not in this interval, I'm not going to list it as a critical value. Okay? So, our only critical points here are just going to be t equals 2.386967 dot dot dot. However, if this interval was something like -1, 24, then we would also need to list t equals 0. But we're not going to do that because we didn't get that interval. Okay? So that's an example of when it doesn't exist. Okay, so what are the endpoints of the interval on which e is defined? Well, that's just going to be 1 and 24. Okay, so based on the list we made in problem 4, what was that list? We said that global minimums and maximums will occur either at critical points where p, we have f prime of p equals 0, or at points where f prime of p is undefined, or at the endpoints a and b. Okay, that's where we should look for a minimum of this function. All right, So now what we're going to do is write down all the values of t where the global minimum of E might be. And our table is going to look something like this. We'll put E on the right-hand side, and we'll put T on the left-hand side. And there's a few places I should check. Okay, I should check all my state champs to see if any of them are the national champs, right? That's what I'm doing here. So I'm going to check the critical point, 2.38 ... I'm also going to check the endpoints, 1 and the endpoint 24. Okay, we'll take this part a step further and actually find where is the global minimum of E. So what I'm going to do next is take all these values here on the left-hand side, and I'm going to plug them straight into E and figure out how high is the graph of E at each of those points. So I think I already did this, if I'm not mistaken. Yes, I did. So it's like 0.89511. Um, 1.95 and then 6. Okay, so this is our table that we got. We took all of the possible candidates for a global minimum and we put them in this table. Am I ready to decide where the global minimum of this function E of t is on the interval 1, 24? Anything else that I need to consider before I go ahead and pick one? I'll take the silence as a no. You're right, there's nothing else to check. We just have to find out which of these numbers is the smallest number on the right-hand side. Well, it's going to be this one here, right? That's the smallest number. So we can say with confidence E of t reaches a global minimum at the point 2.38 ... comma 0.89511 on the interval 1, 24. Questions about how we did that? Okay, so remember when we're talking about a global minimum or a global maximum, we always want to refer to where we are looking. Okay? What is the scope of our search? Are we looking for the global minimum in some small interval, some larger interval, or does our interval include all the critical points of F? We don't know. We gotta take it as a case-by-case basis depending on the interval on which we're searching. Okay, so there's one last thing I want to say. And now I forgot what it was. Oh, yeah, that's right. I forgot. I did a picture of this thing. Okay, so this is what this actually looks like if you were to graph it. So let me draw visually what we were doing. We took our interval from 1 all the way out to, I don't know, 24. It just keeps going in that same kind of direction like this. Okay, and so we consider all of these x values which lie on this line here. And we look for the place where our function has the lowest point. Okay? There's 3 places that I have to consider. I have to consider the height of my function at the endpoints. and I have to consider the height of my function at the critical point, which remember my critical point was 2.38 something. So let's go to there. It'd be like right here. Okay? So the table that I made listed the t values from the t-axis on the left-hand side and these heights of these points on the right-hand side. If I want to find the global minimum, I find the place where the height of my function is the smallest number. So that happened at our critical point, 2.38, and it's visually apparent on this graph. Any questions about finding global minimums and maximums on an interval? If not, we're going to move on to the next section. So, any lingering questions about that? Okay. How am I doing on time? God, time always goes way too fast in this class. All right. So now what are we going to do? Okay, great. Applications. So we're not really going to learn anything new today. All we're going to do is reconcile this new understanding of minimizing and maximizing functions to our understanding of marginal profit, marginal revenue, profit, revenue, cost functions, and that sort of thing. Right? We can imagine how we're going to try to apply this. When I'm running a business, I want low costs, right? So I might try to minimize my costs, or I might try to maximize my profits. Okay? So the way we're going to do that is just by applying this critical point theory to these functions. It's going to be a straight application. Okay, so let's take this graph here, which is graphing our revenue function R of Q and our cost function C of Q, of supplying a quantity Q of a good R given in the following figure. So we want to estimate the maximum profit and the quantity Q which maximizes profit. Well, it looks like it's pretty much already drawn on here for us, isn't it? So remember, this green line here, maybe I'll make it blue. This blue line, it's already kind of blue. That's our revenue. And this red line, red curve, is our cost. So if we're in a situation where the cost function is higher than the revenue function, that's a situation where we're losing money. Okay? And this height here of this red bar is going to be the amount of money that we're going to lose if we produce the number of items which is at this red dot. Okay? And before we drew green lines when we were talking about making money, right? And we said we like green lines. We want the green line to be as big as possible. And it looks like that's going to happen right here at this big green bar. Okay, so when does that happen? That happens when Q is equal to 140. And we have a corresponding revenue of 80,000 and a corresponding cost of 60,000. So maximum profit, I know pi of Q is equal to R of Q minus C of Q. And pi of 140 is equal to 80,000 minus 60,000 equals 20,000. Any confusion so far? Okay. The important thing is keeping which one straight, right? We need to make sure that we have green lines when the revenue function is on top, and we have red bars when the cost function is on top. Okay, if you switch that up, you're going to get a very different and incorrect answer for this problem. Okay, so we want revenue to be bigger than costs. We don't like costs. Okay, so certainly R of Q is greater than C of Q at that point. That's what I was just talking about. Now let's compare the marginal revenue and the marginal cost at the value Q. So let's consider, what do these tangent lines look like? Put one in right here. Looks something like that. If we drew another tangent line right at this point, it would look kind of like that. Is there anything particularly interesting about these tangent lines? Kevin?
They look like they have the same slope.
They look like they have the same slope. What's the word we use for lines with the same slope? Parallel, right? Yeah. So these lines are parallel. I hope I spelled that right. Okay, so what is that saying? We know that the slope of that curve is given by the slope here of this curve is C prime of Q. And the slope of this top curve is going to be R prime of Q. If the slopes are the same, then these two things are equal. Okay? Now, why is this going to, in our case, correspond to a maximum profit? Well, remember, we have pi of Q is equal to R of Q minus C of Q. So, by this difference rule, if I want to find pi prime of Q, it's going to be equal to R prime of Q minus C prime of Q. Oh, holy shit. Oh, I am recording. I thought I didn't start the recording for a second. Okay. That would have been bad. All right. Crisis averted. Okay. So, what's going on here? R prime of Q is equal to C prime of Q. So, what's pi prime of Q going to be? Yeah, 0. If we have two numbers that are equal to each other and we subtract them, like 7 minus 7 or 10 minus 10, we get 0. So this is going to be 0. So at least we know that at that point, Q, you have a candidate for a max. Now, if we wanted to really specify that it was going to be a maximum, we could go ahead and look at the second derivative of these two functions. We know that R double prime is going to be, well, we'd have to make some comparison. I guess we won't look at that. We can tell just from looking at the graph, but pi double prime will tell us if Q is a max. Or we could use the first derivative test, so on and so forth. Okay, so that's when we're going to maximize our profit, which is what we're trying to do in most of these problems, okay? So we want to maximize profit. It comes down to finding where is R prime equal to C prime. Okay, so find the quantity which maximizes the profit if the total profit is given by pi of Q equals 600Q minus 4Q squared minus 17,000, where Q is the quantity. Well, I just want to maximize this profit function here, okay? So I'm just going to take the derivative pi prime of Q which is going to be 600 minus 8q. And I'm going to set it equal to 0. Do I need to worry about the DNE case? No, why not? Because pi of q is a polynomial. Very good. So let's find the critical points here. What are we going to get? We're going to get 8q equals 600. So q equals 75 is a critical point. Let's check the second derivative. Pi double prime of q, what's that going to be? Just negative 8. So pi double prime of 75 is going to be negative 8, which is a number which is less than 0. So we have a critical point where the concavity or the second derivative is less than 0. Is that telling us we have a min or a max? Yeah, do you agree? Okay, so 2 votes for maximum. And can you justify your answer? As for why that's going to be true? By referring to the concavity by chance?
Is it being concave down?
Yes, very good. It's going to be concave down. And if we draw the word down, that n there kind of looks like a maximum. Okay, so again, this is that confusing thing where it turns out that negative concavity corresponds to a maximum. We're used to thinking negative means decreasing, means small. So don't let that intuition trip you up. Draw the picture. So we have a max at q equals 75. More specifically, we have a local max. But we have a constant concavity, right? We have pi double prime of q is equal to negative 8, which means we're concave down for all time. If we're concave down for all time, there's only one place where there's going to be a maximum. If we had a graph which looked more like this, there's no way for it to go back up without the concavity changing to being something other than negative 8. So that's how we can say that with authority that this is going to be the max. But they didn't ask us to do that, so we're just going to say that. Okay, so based on your observations in problem 1 and 2, write down 2 ways in which you might locate the quantity Q which maximizes profit. One will involve the marginal revenue and marginal cost, and the other way will involve the marginal profit. Well, way number 1, find Q's such that pi prime of Q equals 0. Way number 2, find Q's such that R prime of Q equals C prime of Q. Are there any questions so far about this profit stuff? Could be about the graph problem all the way up to this kind of explanation of these guys. Okay, we'll keep on trucking with more examples then. All right, we're supposed to find the quantity which maximizes the profit if the total revenue and total cost in dollars are given by these two functions. So let's use way number 2. I mean, it's basically just way number 1, right? We're going to compute R prime of Q. So that's going to be 5 minus 0.006 q. And C prime of q equals 1.1. Okay, so we'll use way number 2. We'll find the q's which make R prime of q equal to C prime of q. So we want to solve R prime equals 5 minus 0.006 q. And we set that equal to 1.1, which is C prime. Okay, we set C prime equal to R prime. Okay, so I'll move the 5 over, or I'll move the 1.1 over maybe, and I'll move, so we'll have 0.006 q equals to 5 minus 1.1, that's 3.9. And now we'll divide both sides by 0.006. We'll get q equals whatever that is, 3.9 divided by 0.006 equals 650. Okay, so let me reread the question and be very particular about what we're asking here. We're supposed to find the quantity which maximizes profit if the total revenue and costs are given by these functions, where Q is the quantity and 0 is less than or equal to Q is less than or equal to 1,000 units. So our problem here is to find a global maximum and a global minimum on an interval. There's a few places where I might hope to find the global maximum and global minimum. One of them is going to be this point here that causes pi prime of q to be equal to 0. Where else might I find a global maximum or a global minimum? The endpoints. Anywhere else besides the endpoints? And where f prime is equal to 0? There's one other place. Remember, we got f prime equal to 0, or at the endpoints, or where f prime doesn't exist. Thank you. Why don't I have to worry about f prime not existing here? Well, R of q is a polynomial. C of q is a polynomial. If I subtract these two functions to get the profit function, I take two polynomials and I subtract them, I get another polynomial. Do you guys believe that's true? If you take two polynomials and you subtract them, you're going to get a polynomial? Why don't we spend some time talking about why that's true? If I have something like ax squared plus bx plus c, that's a polynomial. And I add to that a dx squared plus ex plus f. What am I going to get? I'm going to get a plus d times x squared plus b plus e times x plus c plus f. Still a polynomial. All right. So, we should now make a table. Okay, we should make a table. On one side, I'm going to put the values q where I might reach a minimum or maximum profit. 650 should go on here. What else should go on?
0.
and
1,000.
1,000. Okay, that came from the problem. Now, what should I put on the right-hand side of my table here? I'm thinking maybe pi of q, or r of q, or c of q. Which one should go on the right-hand side of my table? Yeah, pi of q. I should use pi of q here because pi of q is what I'm trying to maximize. I want to know, at these 3 points, what's happening to my profit. So on the right-hand side, I'm going to put pi of q. I want to know what the minimum profit is, or the maximum profit. Okay, so now I need to plug into the pi of q function, which, why don't we just write it down what it is? It's going to be r of q minus c of q. So we get negative 0.003 q squared plus 3.9 q minus 300. Okay, so if we plug in 0, we're going to get negative 300. Now let's do some computing here. 3.9 times 1,000 plus 0.003 times 1,000 times 1,000 equals minus 300. All right, I think I got 600 for 1,000. If we do 0.003, multiply that times 650 times 650 plus 3.9 times 650 minus 300. Sweet. We got 967.5. Okay. So in red, let's highlight our minimum possible profit. It's going to happen when pi of q is the smallest number. The smallest number on the right-hand side is negative 300, and it happens when we produce exactly 0 items. So let's not produce 0 items. That's a bad idea. We're going to lose $300. Okay? In green, let's highlight the maximum profit. Well, the biggest number on the right-hand side is 967.5, and we're going to reach that profit if we produce 650 items. So the quantity of goods that we should produce is 650, because that will give us the largest profit, and we like money. Any questions about this problem? Okay, so again, this was a global minimum and global maximum problem. When we do a global min and max problem, we're talking about maximizing a function on an interval. The places we need to check are all of the critical points of our function, which happen either when f prime doesn't exist or when f prime is equal to 0. We didn't find any places where f prime didn't exist because our function was a polynomial. The other places that we had to check besides the critical points were the boundary points. So we took all of our critical points and all of our boundary points, and we put them in a table, and those are like our state champs, and now we want to look for the national champs, or the national loser in our case, and find out what's the smallest number on the right-hand side. That's our global min, with the corresponding critical point being 0. And then we find where we have the maximum profit. Okay, how are we feeling? Let's have some thumbs. Is this reasonable, thumbs up. If you're pretty confused right now, thumbs down. Otherwise, somewhere in the middle. Okay. I think that makes me feel okay. All right. This problem was supposed to be taken out. I don't know why it's here. We're not doing that. Nope. Here we go. This problem looks interesting. We'll do this one. Okay, a landscape architect plans to enclose a 3,000 square foot rectangular region in a botanical garden. She will use shrubs costing $45 per foot along 3 sides and fencing costing $20 per foot along the 4th side. Find the minimum total cost. Wow, this is an awesome problem. Okay, with these things I find it's useful to do a drawing before you get started. So let's have a drawing of what the hell is going on here. We have 3,000 square feet enclosed by shrubs and fence. 3 sides have shrubs. Right? 3 sides have shrubs and fencing on the last side. Okay, so what does it look like? It looks something like this. Nope. It looks like this. Okay, so we have fencing on one side and shrubs on the other sides. And we have that the area of this is 3,000 square feet. Very interesting. Okay, the cost of the fencing is $20 per foot. And the cost of the shrubbery is $45 per foot. Great. Okay. So we want to know how much this is going to cost us to do. So we're really interested in this function C, which represents our cost. And it's going to be $20 times the number of feet of fencing plus, why don't I go to green for the shrubbery? $45 times the number of feet of shrubbery. Okay, so what we need to do now is express the number of feet of fencing and the number of feet of shrubbery as a function of x. Okay, and here's how we're going to do it. We're going to have to use this fact that we're enclosing 3,000 feet squared. Okay, so I know that this shape should be a rectangle. Let's go ahead and decide what the dimensions are. I'm going to call this length along the bottom x feet. If I have a rectangle and the length is x feet, well, the length on the top is also x feet. If I know that area equals length times width, if I know the area and I know the length, can I find out what the width is? Yeah, I can. So let's call this y. That length will be y. Okay? And what I'm going to try to do is express all of these lengths as a single variable so that when I plug in C equals $20 times the number of feet of fencing and $45 times the number of feet of shrubbery, it should be a function with just one variable in it. Okay, so here's how I'm going to do it. I know that 3,000 feet squared is the area, and that's going to be equal to the length times width. Well, the length is x, and the width is y. So I can express y as being equal to 3,000 divided by x. Okay? 3,000 divided by x. 3,000 divided by x. So now I can put together my cost function as a function of one variable. It's going to be C is going to be equal to $20 times the number of feet of fencing. How many feet of fencing do we have in this picture? X feet plus 45 times, what is the number of feet of shrubbery which I have? Yasmin?
It would be like 3,000x, two of those, and then plus the x feet.
Yes, very good. It's going to be x plus 6,000 over x. How did I get that? I took the length on this side, and I added it to the length on this side, and I added it to the length on this side. That's the total amount of shrubbery which I have. So the cost of my whole setup is, let's see, we'll make that 65x plus 45 times 6,000 over x. All right. Now, we want to find the minimum total cost. So we better minimize this function. Okay, better minimize this function. If I want to do that, I should find the derivative. It's going to be 65 plus, no, it's going to be 65 minus 45 times 6,000 over x squared. I did the derivative of x to the negative 1 there. The negative 1 came down and got multiplied, and the power became 1 less than it was before, so the power became negative 2. And I want this to be equal to 0. So what is this saying? 65x squared equals 45 times 6,000. So x squared equals 45 times 6,000, all divided by 65. So x is going to be the square root of all that. See here, 45 times 6,000 Divide that by 65. Take the square root of it. Plus or minus 64.45. So, which one is it? 64.45 or negative 64.45? What do we think? Should we put a table? Should we make a table and figure out?
It's the positive numbers.
Yeah, it should be the positive number. Can you explain why?
Because you can't have negative something.
Exactly. I can't have a negative amount of fencing. It's as simple as that. So I'm pretty sure that the answer is going to happen at x equals 64.45. How could we double check that this is actually a max, or a min, excuse me? Any ideas on how to check? Yeah, Ryan?
Plug it into the rectangle and make sure it multiplies to 3,000.
Yeah, the way we've set it up, it will definitely satisfy this area requirement. But my point is, I have a critical point of a function, and I'm not quite sure yet if it's a max or a min. How can I check, Dylan?
The second derivative test?
Yeah, second derivative test would be one way, or the first derivative test would be the other way. Let's use the second derivative test. C double prime is going to be equal to 45 times 6,000 times 2, all divided by x cubed. So in particular, the negative 2 got multiplied down, so this whole thing which was negative before became positive, and the power became 1 less than it was before. And if I plug in 64.45 into this equation, am I going to get a number which is larger than 0 or less than 0? (45 times 6,000 times 2, all divided by 64 cubed). Is that number larger than 0 or smaller than 0? It's larger than 0, which means we have concave up. For concave up at that point, and it's a critical point, then it's going to be a minimum. Okay. Oh, geez, I'm 4 minutes over. All right, somebody should have stopped me. Okay, that's it for today. If you have questions, you can stay after class, or you can come to office hours today from 12 to 1. Yep, no problem. Questions?
Yeah, how did you get to, we have C equals 20x plus 45, and it's like half of the 20x is in a different color? So I'm talking about.
Sure. You're talking about this part right here, right?
Yeah, so how did you get from that to 65x plus 45 over times 6,000 over?
So I distributed the 45 here onto both the x and the 6,000 over x. So when I distributed that, the whole thing became 20x plus 45x. That's where the 65x came from.
Okay.
And then the last part would be 45 times 6,000 over x, and that's how I got this second part.
And you were just, so like that whole time that we were doing that, you didn't even know like if it was gonna be a min? Like we weren't sure?
Correct. I suspected, and here's why. Basically, what we're thinking about here is the cost of doing these various different setups. So one setup might look something like this, really long, with a lot of fencing. And then something in the middle might look more reasonable, like this. Or maybe we have very little fencing and a shitload of shrubbery, like this. Maybe it looks like that. Okay. And my goal is to consider the cost of these setups. Okay. I think you can tell just by looking at it that this one here is going to cost a lot because it's so dang long, right? Really, we're considering sort of the perimeter of each of these things, right? And if the area in each of them is all 3,000, well, when this number, this length here gets small, these lengths have to get huge, right? And so that's going to really drive up our cost. So the reason that I suspected that this middle ground is going to be a minimizer of our cost is because if I consider an extremely long fencing area, if I consider the perimeter of each of these, the perimeter of the two long ones is going to be much, much bigger than the perimeter of the small one, right? So I can kind of visualize, I think that when x, our length, is really big, we're going to have a huge cost. So our cost function might look like this. When x is huge, the cost is really big. When x starts to get really small, that's this case here. Remember, this value x was the length of the bottom. If I consider the really tall case on the right here, it also costs a lot because I have to make so much shrubbery. So I know I'm high here, and I suspect that in the middle, my price is not as much. So that's why I think probably somewhere in the middle ground is where I'm gonna find my minimum, yeah. And in fact, you can see from the second derivative, let's consider this second derivative, 45 times 6,000 times 2 divided by x cubed. If x is any positive number, this number is going to be a positive number, which means that our function is concave up for all time, which is why it looks like this big U shape, right? Yeah. And if I have something which is concave up for all time, the only thing I have to find is just where is that first derivative equal to 0, and that's going to be my minimum.
So you just find like the equation like by doing like you do like the x and then 3,000 divided by x, and that's going to be most of the time like either the minimum or the maximum using that.
Right. So it took a little bit of work to figure out what the equation should be that we're going to minimize, right? Yeah. So we had to come up with a clever way of writing down the cost of our whole operation. So first we wrote down $20 times number of feet of fencing plus 45 times number of feet of shrubbery. Okay? And the point is that if I have a rectangle, and I know that inside area is 3,000, if I decide how long one side is, I know how long all the other sides are because, well, since it's a rectangle, this top one is going to be the same length as the bottom one.
And I have to multiply.
And then if this is, you know, your height here, or width or whatever, then you know that 3,000 equals x times y. So if I decide how long x is, say I decide x is 64, then 3,000 equals 64y, and then I can solve for y. Does that make sense?
Yeah.
So, in particular, if I have this setup, if I know that the area is 3,000 feet squared, and I know that the shape is a rectangle, if you tell me how long one of the sides are, I know all of the dimensions of the rectangle. And so the key here is to write down all of the dimensions of the rectangle in terms of x. Once I know what this length is in terms of x, and I know that this length is x, then if I want to find out how long the shrubbery is and how long the fencing is, it's just a matter of, you know, combining the sides.
So then you create your like area equation and then find the prime of that and set it equal to 0, and that's it.
Not quite.
No.
That would be if we were trying to find the maximum area that we could enclose, or the minimum area that we can enclose. The problem in this case tells us exactly how much area is enclosed. They want us to provide the dimensions of the rectangle which minimize cost. So my job is to write down the cost function and then take the derivative of it and minimize it.
Okay.
Sometimes other problems like this will be framed in a different way. They'll say, I don't know, Mary has 300 feet of fencing and she wants to enclose some area along a river. So here's the river and she wants to use her fencing to enclose a certain area. And we want to know what should the dimensions be to maximize, if she has a certain amount of fencing, what should the dimensions be which maximize the area enclosed? Right? That's another common type of problem for this. But in our case, instead of telling us how much fencing we have and telling us to maximize the area, they're telling us exactly how much area is enclosed, find the ideal amount of fencing and shrubbery such that this is cheap. Okay? And the point was, if we make it really long and wide like this, it's super expensive because the shrubbery line, remember, each foot of shrub costs $45 dang. So if we make it super long like this, it's not going to be good. On the other hand, if we make it too long like this, it's also not going to be good because this is making the shrubbery even longer. So we want to find some happy middle ground where the shrubbery is not too long. We use up a lot of fence, but we don't use up so much fence on one side that we make the other side of shrubbery really long and make that expensive, you know?
Yeah. So I guess my only question is then, how did you get like the I know you, like I get the equation 20 times number of feet of fencing plus 45 number times the number of feet of shrubbery.
Mm-hmm.
But then how did you get like the numbers? Like how did you get 20x plus 45?
Sure. So I said, remember that...
So I know the number of feet of fencing is x, so like the 20x makes sense to me.
Okay.
I get that. I don't understand how you got the green part, the 45 times x plus.
Sure. So it should be $45 times the number of feet of shrubbery, right?
Mm-hmm.
So let's go to my drawing here. I want to count up how many feet of shrubbery I have. I know that this side, on this side I have x feet of shrubbery. I have 3,000 over x feet of shrubbery here, and 3,000 over x feet of shrubbery here. So if I want to know how long this entire green path is, I should count how long is this thing? It's 3,000 over x. I should add the length of this, which is x, and then I should add the length of this, which is 3,000 over x, right? So altogether, x plus 3,000 over x plus 3,000 over x
Okay, yeah.
is the addition of the length of the sides here, which is x plus 6,000 over x.
Makes sense.
Yeah, no, good question. Doing these fencing problems the first time, it's really difficult to decide what the dimensions should be, and this game of getting an equation for c, I mean, once we're here, we know exactly what to do.
Yeah.
We just take the derivative and find when it's 0, right? But the bulk of the problem was really in figuring out, how do I express number of feet of fencing when I haven't decided yet what the number of feet of any of the sides are going to be? And the key thing is to say, okay, suppose I did decide how long one of the sides was. Well, then I would know how long the other two sides are, or the other three sides are, because I know how much area is enclosed. And I know the fact that this shape has to be a rectangle.
Yeah. Okay. Thank you.
Yeah, no problem. Any other questions about that?
Not really, no.
All right.